Welcome to our presentation on artificial neural networks. Our group consists of Vanetta, Weibin, Joan, Xiaoming, and I, Zhenghua. Let me start off this presentation by introducing you to the topic. Imagine some everyday tasks that we may have to deal with. When you're looking through old photos, you might want to recognize whoever appears in these photos. Or maybe you want to read the phone number that your crush just passed to you. You might want to drive your car to run some errands too. Most of these tasks sound rather easy for humans, or somewhat difficult in the case of driving cars, but if you wanted to get computers to perform these seemingly trivial actions, and potentially do them much better than we ever can, how would we go about doing this? The answer lies in artificial neural networks, a recent development that is shaking up the machine learning scene. A quick history on neural networks before we continue. The concept was actually first developed all the way back in 1943, and its first implementation in hardware was completed in 1954 by these two gentlemen on the right. It was a rough start though, as these networks were limited to very niche problems, the results were slow to compute, and could not even get much better than results than other computer methods already available at the time. It will not receive widespread attention until 2012, when it underwent a rebirth of sorts. That year, the potency of neural networks were proven when variations of it won in several prominent competitions, and has only grown in popularity and competence with increases in computing power and sophistication of the algorithms. So how does a neural network work? The concept is roughly based on neurons of the brain and how they work. When a neuron reads electrical signals through connections to other neurons and sends out its own signals to other neurons down the line, a neural network similarly processes inputs and returns outputs that we interpret as results. A neural network first needs a way to compute results from the input is given. A common way of doing this is to apply weights to each input, which usually ranges from 0 to 1, and put them through a function to get a number also ranging from 0 to 1. The larger the weight of an input, the more that the input each contributes to the overall result. This result can also be adjusted manually with a bias if so desired. Neural networks don't just consist of inputs and outputs. Often, they will also include hidden layers that serve as a bridge between inputs and outputs. These hidden layers values are similarly calculated from the layer preceding it and are then fed into the next layer. This goes on right from the input until the last layer, the output, is reached. Training a neural network to solve problems consists of several steps, beginning with forward propagation, with a set of training data consisting of the actual inputs and the expected results. The weights of the neural network links are set randomly, and from there, the input data is fed into the generate outputs. Okay, so we made the neural network give us results, but how do we make the network give answers that are not just blatantly wrong? This is where the concept of cost comes in. Cost is a formula to tell the neural network just how good or bad the result was by comparing it with what was expected of the input. Bad results will usually result in a high cost, whereas results that are very close to the real result is given a low cost. Once the cost has been calculated for an output, the magic happens in the next step, which is backpropagation. Since the cost for a single step of inputs is ultimately affected only by the weights and biases of the neural network, it is possible to interpret how to adjust these values to get a lower cost and better output. By working backwards from the cost value, the weights are changed slightly from the output layer all the way back to the input layer. So the training cycle becomes putting in data with a random set of weights into the new neural network to get results, i.e. forward propagation, calculating the cost of the output compared to what was expected, and then adjusting the weights accordingly using backpropagation. The process is repeated in small steps until the output resembles the expected result more closely and the cost does not change noticeably after more training cycles. After training the neural network, the next thing to do is obviously to test your neural network to see if it can produce accurate results from new sets of data that it has not seen. By doing this, we ensure that our spanking new artificial neural network can be applied to all the scenarios it can encounter.
Now we'll move on to cover the exciting applications of neural networks, and the first of which is in facial recognition. So what exactly is facial recognition? Facial recognition is a visual pattern recognition problem. It is essentially a system with an input and an output. The input is an image containing one or more faces. With this input, the system can then generate an output, which is the identity of the face. In order to produce this output, the image will go through 4 different steps: face detection and tracking, face alignment, feature extraction, and finally feature matching. Initial attempts at facial recognition divided the face into different landmarks, which are known as nodal points. These include the location of your eye sockets, nose width, and distance between your eyes. Each face is then given a unique code. However, for a good match to occur, the images of the face must be almost identical with what is in a database. This is not possible in real-life applications because our faces are in constant flux due to aging, pose, illumination, and our emotions. Given these images, we can easily identify that they belong to the same person. However, this task proves to be difficult for computers. In fact, our human brains are one of the best at facial recognition. As such, scientists have looked at implementing neural networks for facial recognition because they are similar to our human brains. Researchers have shown this by showing pairs of faces to 33 epilepsy patients who had electrodes implanted into their brains previously. Some pairs of faces caused similar brain activity, while others resulted in dissimilar ones. The same face pairs were then shown to neural networks, and the reactions of the human brain and the neural networks were plotted on the graph as shown here. As we can see from the graph, most of the face pairs are close to a diagonal, which shows that there is a strong parallel between the way the human brain and neural networks function. Where exactly are neural networks being applied to facial recognition systems? Well, firstly, they are applied in the face detection process to identify faces in images. One approach of this is known as the region-based approach. A search is carried out to generate pools of regions which may contain one or more faces. These proposed regions are then input into a neural network, which will tell us whether there is a face in the region or not. Another method is known as the sliding window approach. An image pyramid is created using multiple scales of the original input image. A window will then be used to scan the images at the different scales, and face detection scores are given to each window. This process is similar to what you can see in the GIF in this slide. The detection of faces from the various scales can then be fused to give the location of the faces in the original image. Neural networks can also be used for feature extraction. They can be trained to identify the different features on our faces. This is an important step because the features extracted will be used to assign a bunch of numbers to each face, thereby encoding it. When various features such as eye centers, nose tips, and mouth corners are detected, the face can then be normalized for further analysis. An example of this normalization is the alignment that takes place in this photo here. There are various methods to extract features, and one method is to fuse information from different layers within the neural network. An example of this outcome can be shown in the diagram here, where the red dots represent the features that have been extracted. Neural networks are also being applied to the last but crucial step of facial recognition, which is facial identification and verification. There are 2 steps in this process. The first step is facial representation, which focuses on extracting unique features from each face. The second step is classification, which aims to assign the face in the image to a particular identity. One approach of using neural networks for facial representations is known as FaceNet. A large dataset of facial images will first be used to train the system. In general, neural network models are trained using an optimization process that minimizes an error. And FaceNet does this by minimizing what is known as the triplet loss function. This involves training triplets of faces, which include both matching and non-matching faces. An example is the set of 3 faces here. One image is known as the anchor image, while the matching face is known as the positive image, and a non-matching face is known as the negative image. Through the deep learning process, the distance between the anchor and positive image is decreased, while the distance between the anchor image and a negative image will be maximized. This allows for faces of the same identity to appear closer to each other than faces of another identity. In the case of this example, images of Obama will be closer to each other as compared to that of Marco. Once the entire system has been trained, the same process can be applied to a test set of data to test the accuracy of facial recognition. Indeed, neural networks are important for facial recognition systems, and it surely is exciting to see how this field will continue to evolve.
Now, moving on to natural language processing. The reason why artificial neural networks are used for natural language processing is because artificial neural networks can perform well when rules are difficult to pen down in a rigid and logical manner. Language, with its ambiguous and imprecise rules, can then be well tackled by artificial neural networks. Natural language processing is particularly relevant due to the large amounts of language-based data generated today. Natural language processing makes it possible for machines to analyze and interpret these data, paving the way for useful applications such as automated fake news detection on social media platforms. However, natural language processing is not a straightforward task and has many challenges of its own. Firstly, language-based information are considered unstructured data, as the structure behind languages are rather complex and are not in easily definable forms. For instance, the analysis of different texts cannot be done the same way. Some may require us to interpret the entire text holistically, while some suffice with understanding each sentence individually. Next, due to the different format of different languages, not all languages can be analyzed in the same way. For instance, it might be practical to analyze English words individually, but such an approach is impractical for other languages, like in Mandarin, where individual characters are now composed to separate words. Finally, most languages have a large vocabulary which results in the curse of dimensionality. The curse of dimensionality is as such. If every word is taken to be unique and unrelated to all other words, that is, a distinct variable, based on the English language alone, there will be 1 million words, with an average person using 20 to 30,000 words. Thus, a large dataset will be required to properly train the model. If we want to train the model on the words occurs in 10 different sentences, we require 10 million different sentences. Thus, distributed representation is used to reduce the words into a more manageable number of dimensions. In this way, the similarity between words can also be captured. In this example, the words in the English vocabulary are captured within 22 dimensions, solving the curse of dimensionality. We can also see that the words king and man, women and queen share similarities with each other, indicating that the meanings can also be captured within the dimensions. To perform distributed representation, methods such as continuous bag of words are used. In this method, the conditional probability of a target word is computed given the context words surrounding it. The skewed-gram model does the opposite, predicting the surrounding context given the central target word. However, using individual word embeddings cannot properly represent phrases. For instance, the phrase hot potato has a meaning that cannot be deduced solely based on its constituent words, hot and potato. For these methods, window size is also an important factor, as some words such as good and bad might share the same embedding as their context words are likely to be similar. In this neural network embedding model, each node in the input layer contains a word in the window where they will be transformed in the hidden layer into a vector representation. Another method is to use character embedding, which classifies individual characters instead of whole words. This is particularly useful for languages with large vocabularies, as it tackles all vocabulary words. For instance, this method is useful for Mandarin, as the individual characters are not composed to separate words, thus avoiding word separation. Another method is to use contextualized word embedding, which is good for polysemic words, that is, words with multiple meanings. Encoding words based on its context will lead to separate vector representations of the word. Another method is the use of bidirectional language. For example, the two sentences, the bank will not be accepting cash, and the river overflowed the bank, will lead to two separate vector representations of the word bank. Using the bidirectional language approach, the word bank translates to two different words in French, representing the financial and geographical meanings. After performing distributed representation, the results can be used in a convolutional neural network to determine the label, that is, the interpretation of the sentence. Firstly, the individual words in the sentence are used as inputs. Then, based on the word embedding used, the individual words can be represented as vectors and the sentence as a matrix. Convolution is then done to produce new features. This process is random and is optimized. Max pooling is then done to ensure a fixed length output, which will then be softmax classified to produce labels for the sentences. This method is effective if the semantic clues can be captured in the contextual window, but is limited in modeling long-distance contextual information. Recursive neural networks, on the other hand, mimics a recursive way language has, where words and subphrases combine in a hierarchical manner. To determine the label, the network combines words from the bottom up. In this example, the sentence, "There are slow and repetitive parts, but it has just enough spice to keep it interesting," has its label significantly affected by the word "but," which caused the network to be confident that the sentence is positive. Currently, AI assistants like Google Home and Alexa uses natural language processing to assist us. A vast portion of data today are unstructured, and it is estimated that the amount of unstructured data will continue to increase exponentially. Natural language processing serves as a model for the interpretation of unstructured data, and natural language processing could serve to assist us in understanding business sentiments and interpreting healthcare notes in the future.
Application we have is regarding self-driving cars, and I believe that all of us is not unfamiliar with this topic, given that such vehicle is even being tested in NTU. So why is self-driving cars so important? Firstly, it is due to the safety reasons, as thousands of people die in traffic accidents every year, and self-driving cars could potentially reduce the number as it could reduce human errors. Next, equity is another major consideration. Self-driving cars could help mobilize individuals who are unable to drive themselves, such as the elderly or disabled. Lastly, self-driving cars can greatly reduce the need for manpower for taxis, bus, and even Grab. This can reduce costs and stress on manpower needs, especially in small countries like Singapore. Self-driving car system can generally be divided into 4 blocks: sensors, perception, planning, and control of the car. The car is sensing the world using many different sensors mounted on the vehicle, such as camera and GPS. The information from the sensors is then processed in a perception block into meaningful information. The planning block then uses the output from the perception block for behavior planning. Lastly, the control block ensures that the vehicle follows the path provided by the planning block and sends control commands to the vehicle, such as increasing the speed or stopping the car. Self-driving cars can recognize and react to their environment in real time, allowing them to safely navigate using deep neural networks or DNNs. Rather than requiring a manually written set of rules for the car to follow, such as stop if you see red, DNNs enable cars to learn how to navigate on their own. Example, if a DNN is shown multiple images of stop signs in varying conditions, it can learn to identify stop signs on its own, which makes DNN important as cars can learn from their own experiences. An entire set of DNNs, each dedicated to a specific task, is necessary for safe driving. This task covers everything from reading signs to identifying intersections. In order to process multiple DNNs, a centralized high-performance platform is required, and an example is the NVIDIA Drive AGX developed by the company NVIDIA. In a YouTube video published by the company, they tested a self-driving car using DNNs, and at the start, there were many errors such as driving out of lanes and even bumping into trees. But after around 5,000 km of learning, the car showed great improvements and can drive very smoothly, showing the effectiveness of using DNNs. However, currently supervised learning is still the major approach to train self-driving cars. A supervised model is only able to do what it is taught. For example, if a training dataset only contains car, a DNN trained on that set will not be able to recognize pedestrians. Since the number of different traffic scenes in the real world is near to infinity, it is impossible to ensure 100% coverage of the real world scenes. Next, since the self-driving car learned by supervised learning, driving in normal situations will only contribute very little to updating the dataset. For example, NVIDIA trained the self-driving cars for 5,000 km. However, running the car for another 5,000 km in the same situation will not help in improving the detection performance of the DNN. It is rather the anomalies in the data, such as traffic accidents or driving in extreme situations, that are most of interest but are hard to get. To solve the problem, we could use synthetic data and simulation. Scenarios that are important for training but rarely happen in the real world could be compensated through synthetic data and simulation. This can include hazardous weather conditions, example fog and heavy snow, traffic violations, and even animal hazards. Next, transfer learning refers to training DNN on one task and use it for another task. Example, we can train DNNs for detecting cars and then retain it for detecting trucks or even trains. By only fine-tuning well-known model instead of being trained from scratch, we can greatly reduce the amount of training data for self-driving cars. But not least, to add more incentives to learning more about self-driving cars, the self-driving car research industry has reached $16 billion and will continue to rise in the future. Also, many big companies invested heavily in the development of self-driving cars. For example, Waymo, or also known as Google's parent company, spent a total of $3.5 billion testing self-driving cars. Other companies such as Tesla, Uber, and Nissan also invested heavily in the industry. So, if you are interested in joining such big companies, an area you can consider is neural networks in self-driving cars.
While the neural networks that we've been discussing were originally inspired by the actual neural networks of the brain, one of the goals of neural network development is to go full circle, to model biological networks as neural networks. While biological pathways may seem extremely complex, when you boil it down to its bones, they are really no different from any other network we've introduced earlier. The nodes are represented by genes, which contains the instructions, or proteins, which perform the functions. Take the glucose homeostatic mechanism, for instance. Big words, I know, but trust me, it's not that scary. If we take that and strip it down to its essential components, it forms a pattern that looks a lot like any other neural network we've seen thus far. Each gene or protein forms a node, and each interaction between them forms a connection with a corresponding threshold. This neural network can then be trained using the multitude of publications about each component, each stage, each mechanism of the pathway, in order to determine the weight and threshold of each node and connection. Using this general concept, we can create neural networks that can be applied in various applications. So, based on years and decades of research, we have this network of genes that we know are involved in this pathway. But we happen to have these white things here that we suspect are associated with it somehow. So, we investigate this through a neural network. When the red section of the neural network fires off, does this guy respond in a similar way? What about the blue one? If there's a match, then there might be something worth investigating here, and we have an angle to pursue in our laboratories. Does it always work though? Unfortunately, not that well. This method is prone to false positives, as similarities in expression patterns is not definitive proof of a connection. Even if there is a connection, the connection from the guilty by association analysis alone does not provide any information about the relationship. Does this mean that it is useless? Absolutely not. Neural networks assist in processing the absolute deluge of information out there, consolidating them into a meta-review on various topics. Such reviews serve as a guide, highlighting areas of research that show promise and are worth investigating, allowing for a more efficient allocation of resources. It is better for a project to fall apart in its first week because the literature does not support the hypothesis than for it to fall apart in its 100th week when a fundamental error is discovered. It saves money, it saves time, and it allows everyone to move on to find the next big thing. Such neural network analysis raises the bar to start research projects by giving researchers access to better information to evaluate the validity of the hypothesis before they embark on a new ambitious project. Building on this concept, the Deep Cell project has created an extensive neural network that modeled every known gene, protein, and interaction in a yeast cell, effectively creating virtually simulated yeast. Through this, we can manipulate specific genes and proteins, increasing or decreasing their expression to see the overall effect it has on the yeast cell, and through this, gain some insights about basic cellular function. Such cell simulations could revolutionize the way that we approach drug and disease research by revealing the full extent of the impact that our drug is having on the organism. Every gene, every protein, every minute detail is laid bare to us in a smooth and efficient manner. As we develop better computational tools and develop a better understanding of complex biological pathways, we might one day find a way to perfectly model a virtual human body for drug testing. This will guide our human trials for drug research better, developing drugs on a more efficient timeline with less human lives lost in testing. What else could we possibly want? While that may be a long way in the future, in the present, neural networks have been explored as a diagnostic tool. A group of researchers have developed an image recognition neural network similar to the facial recognition application discussed by Vanetta earlier. By applying the same principles, we can identify various defining characteristics in cells that are telltale signs of disease. The team identified and trained their neural network to be able to classify images of blood cells to identify each individual cell and provide a diagnosis on whether the patient is suffering from sickle cell anemia. While this may be a simple application with limited usefulness, after all, we have better ways of doing it, it paves the way for groundbreaking work in future by proving that the theory is sound. Not only does this technology have the potential for greatly reducing errors in diagnosis, it can also extract critical information in a highly efficient manner. Imagine how much better we would be in combating the COVID-19 outbreak if we had a test capable of delivering accurate results instantaneously. With biological networks, the only limit is our imagination. If we can dream it, we can pave a road that will lead us there. If we can overcome the technological and informational barriers in our way, we can certainly revolutionize the way that we approach medicine. So to conclude our presentation, artificial neural networks have the potential to revolutionize society as we know it. As we overcome the technological and informational hurdles in our way, novel developments will advance society in various directions, leading us into a new age of information technology. Being aware of and keeping up to date with the latest developments at the forefront of innovation is absolutely essential in this modern society. Not only will this knowledge help highlight novel tools that can improve your life, it will also identify areas for improvement that you can use to stay relevant in this ever-changing landscape. With the development of artificial neural networks, the world has changed and will continue to change, and we can either advance with it or get dragged along by it.